LAH will take out the carboxylic acid, and you will end up with the primary alcohol, and you go through the aldehyde. And the mechanism here is very similar to what you'll see again and again in this chapter. You will see this idea of replacing the leaving group. These types of carboxylic acid derivatives have a leaving group attached. The aldehydes and ketones did not, and that would be the big difference in their chemistry. So we'll see today now that we can do these types of reductions quite easily, and we can do a very similar type of reduction using BH3. Now this has a lot of use because it is selective. And I will put an asterisk next to this one. I'll talk about it for a second, then I'll show you the mechanism that is thought to happen, and I'll then tell you that you don't need to worry about that mechanism because it's horrific. This is a useful reagent because it reduces carboxylic acids also down to a primary alcohol, but it doesn't go after ketones. Right? That's kind of counterintuitive. If you use LAH, the ketone would go first, then the carboxylic acid would go, and you reduce both of them. But BH3 is selective. BH3 is useful because it only goes after carboxylic acids, as you can see at the bottom, and it doesn't go after the ketone portion. Right? So the mechanism for this must be something a little bit different. What I did this morning was have a look at Henry Zerpa's interpretation of this. Henry's a great guy. He's a professor at Imperial College in London. Great sense of humor, brilliant chemist, and he blogs on chemistry and sort of controversial things in chemistry about mechanisms and stuff like that. So he does computer type stuff, he does calculations, he works out reaction profiles, he builds models and minimizes those models, kind of like we're doing in the honors part of this class. And he comes up with an interpretation. And already it's kind of getting kind of fun, isn't it? You can see all these different graphs and things telling you something about the mechanism. And he and a bunch of his colleagues who are running blogs and sort of going backwards and forwards have come up with this for how BH3 reduces a carboxylic acid. And it involves boron acting as a Lewis acid, as you expect, and it involves boron introducing H-, as you might expect. But it gets kind of hairy around here, I would say. All right? You're starting to look kind of, it's difficult. And it's in the realm now of inorganic chemistry, I think, and it's probably beyond what we want to worry about. But he's quite happy that this now involves a four-membered ring. Those things are strained. And down here, a four-membered ring and a four-membered transition state next to each other. That's kind of fun. And eventually you end up with, ultimately, a primary alcohol. So put a little asterisk next to that. If you're interested in these things and want to read the blog, if you're going to be a chemist, it's the type of thing that, is light reading on a Sunday morning. Have a look at this stuff, and it's very interesting in terms of interpretations. So I would suggest that on that particular slide, don't worry too much about a mechanism. Worry about what it does, but not necessarily how it does it. Okay? So BH3 is useful. You can get rid of a carboxylic acid quite quickly. Now, we have to start thinking about the overall picture. Okay, so just to get us started, to get us to think about where we are right now, what we just did was reduce. And reducing changes the fundamental property of the molecule. You've gone from a carboxylic acid over here on the left, which has a carbon here at a +3 oxidation state, and you went over here to a carbon that looks like it's a -1 oxidation state. You've definitely changed the oxidation state. And fundamentally, you've gone from one family to another. You've gone from the carboxylic acid derivatives, and you've ended up in the alcohols. So that's a move between different families. What we need to do for the rest of this chapter, really, and a lot of the next chapter, is worry about reactions in which we don't actually change the oxidation state. We simply swap out whatever the leaving group happens to be for some other piece. And this is fairly straightforward, except there are many examples of the different piece. And the mechanisms will be very similar, but with different leaving groups and stuff like that. So we'll spend a lot of time now talking about carboxylic acid derivatives. Carboxylic acids themselves you can get from nature. We showed that on the first slide. And we talked about their physical properties. They're quite high boiling and things like that. But they're then used to make other things. Okay? They're then used to link things together. And the difference with these types of reagents on the right-hand side of the slide is that you're bringing in other pieces. You're linking things together, other carbon pieces. So we'll see now that this functional group, what we call the acyl group, remember this piece here is an acyl chloride. Okay, that's the acyl group. We can join things to it and use this as a linker. So when we talk about esters and polyesters, or we talk about amides and polyamides, this is getting into polymer chemistry and how you link things together to make useful materials. So at the top left, I have something called an acid halide. We could also call it an acyl chloride or an acyl halide. We have an acid anhydride. We did talk about these way back in terms of functional groups. You've probably forgotten them, but we'll remember them now. Acid anhydrides, you have a mirror sort of plane in the middle here where the left matches the right quite often, or not if it's not symmetrical. Esters will be very useful. And then we've got the amides. And we've got this sort of continuum of reactivity. We'll say that acid chlorides and anhydrides are super reactive, esters are less reactive, and amides are the least reactive of all. And we'll explain why in a second. And then I think I mentioned this on Wednesday. The nitrile fits into this family. It doesn't look an awful lot like any of the compounds above it, but the carbon here is at the same oxidation state as the ones above. I've got a +3 oxidation state down here, and all of these are at the +3 oxidation state. So it does actually count as an acyl group. Methylbutanoate smells like pineapples, apparently. If you like pineapples, that's what you're smelling. And butyl acetate smells like pears. And esters actually are very common in perfumes and stuff like that because they do have these nice odors. Now, at the bottom, we've got the sort of ultimate linkage, which I think you'll spend a lot of time with in biochemistry and a little bit with me at the end of this term, is how amides are used to link proteins together. And it'll make sense in a minute when I tell you anhydrides are quite reactive, so you don't want an anhydride necessarily in a biological system because it will react and break down. And if you want something that's robust and that will last, you want to make it into an amide, because amides are the most stable of the linkages. And then if you think about the intermediate things, you have esters and you have other types of derivatives, and you can play with the reactivity of these things depending upon what you want in the system. So nomenclature is pretty dry, so we'll fly through this stuff. It's all related to the sort of parent carboxylic acid. On the left, I have acetic acid, and so this should be acetyl bromide or acetyl chloride, depending upon what we've got attached there. Benzoic acid becomes benzoyl chloride. You can see here now the YL component here is telling you that this is a sort of a radical piece. It's a substrate attached to a chloride. So you have sort of a substitutive type of nomenclature in which you recognize the piece and then you just call it a chloride. At the bottom, we've got some awkward ones in which it doesn't quite fit in terms of the size of the cycle or the length of the chain. You can see here we've got a cyclohexane carboxylic acid, which becomes cyclohexane carbonyl chloride. That to me is kind of clumsy, but that's the way it's done, if you can't come up with a simple fragment. So you're looking for this sort of idea of halide, obviously, to say whether it's an acyl halide or not. And related to those are the acid anhydrides. Acid anhydrides are very, very powerful acylating reagents. You can use them instead of acyl chloride, for example, in the Friedel-Crafts reactions. And we'll find now that this type of group here serves just as a leaving group. We'll be able to break that thing off and it become resonance stabilized, which is quite a good leaving group. So you'll get used to these names, especially if you take biochem. Acetic is 2 carbons, so if I condense those 2 pieces together and make acetic anhydride, basically 2 of these molecules react together to give this. What would the byproduct be of that? Think about if 2 of these molecules and all their atoms join together to give this piece, what's missing from that? What's the byproduct? Water. Sorry, water. And that water then is the idea of anhydrous. You've dehydrated. It's now an anhydride. You took the water out, so it's now an anhydride. Succinic acid you'll see a lot of in the future, I would imagine. Succinic anhydride is fun because you've tied this thing together into a cycle, and that gives you succinic. You'll see that in biochem. If you don't have a symmetrical system, you've got to just be careful with this thing, do it alphabetized and sort of come up with the fragments. This looks like benzoic acid, that's where the benzoic piece came from. This looks like acetic acid, that's where the acetic part came from, and it's an anhydride. You couple those 2 things together, that's what you get. So you will need to know, have a good idea of how this works so that we can discuss these things quite quickly. And on exams, I'm not going to give you any points for nomenclature necessarily, but I'll ask you in a question, start out with this material, it's an ester or it's an anhydride, you need to know how to draw it. So esters, we'll spend most of our time on things like esters and things like amides. Esters here, acetic acid becomes ethyl acetate, and this is important to know because you can see now the ethyl group is the R group. The ethyl group is the component on the oxygen that is the, looks like it's singly bonded. So ethyl acetate, acet, comes from the 2 carbon piece from acetic acid, and 8 at the end tells you it's an ester. All right, so ethyl acetate, sodium benzoate. Ethyl acetate, or what did you make in lab? Something like isopentenyl butane, something like that. We can see here malonic acid. You will deal with a lot of this in chapter 22. Chapter 22 is my favorite chapter, and we will spend a lot of time talking about the use of these things in synthesis. So malonic acid has 2 carbonyls attached, 2 carboxylic acids. The 3 carbon piece is derivatized as malonic, and then you put 2 ethyl groups on the end of there, you get diethyl malonate. So the take home from that is the R group on the ester is the first part of the name, and the 8 at the end tells you that it's going to be an ester. Fairly simple. Down at the bottom again, awkward examples, clumsy, cyclohexane carboxylic acid, you make the ester over here, methyl cyclohexane carboxylate. I'm probably not going to push it that far. That to me is sort of clumsy and difficult to learn, but the ones above it probably you could have a go at. Amides, you will need to know a lot about amides if you're going further with any chemistry. Acetic acid to acetamide. That's kind of an abbreviation, but there you are. The word amide gives you a clue. It's an amide. Some people call it an amide. Most of us call it an amide. Benzoic acid becomes benzamide. That's kind of abbreviated. And down at the bottom, cyclohexane carboxamide. So, there's a clue in the name. As long as you know what an anhydride is, or what an amide is, or what an ester is, you should be able to work out logically the fragments that are involved. So, amides themselves get to be very, very useful because the nitrogen, as with the imines and the enamines, the nitrogen has more valences than oxygen. So if you think about a carboxylic acid and an ester, OH or O-methyl, you only have one carbon attached, right? You only have one piece attached to the oxygen. With the nitrogen, you've got a couple of possibilities. You can add this to make what we call a methyl acetamide, and you can make this to call a dimethyl acetamide. Now that's very important in biochemistry and also in sort of polymer chemistry, because you can start to link off different pieces here and bring two fragments together to make quite powerful bonds and quite powerful materials. So the actual nomenclature here, just to be aware of, N-methyl, you need that N in there. And this is something you will see later on in sort of higher level classes. You've got the R group, the methyl group here, is on the nitrogen. If you didn't put the N in front, that methyl group could be someplace else. So that N tells you where it is. The N is on the nitrogen there. So N-methyl acetamide. The parent molecule is acetamide, which would have two hydrogens here. Put a methyl group on there, it's substituted. On the right-hand side, N-dimethyl acetamide, you've got two of these things. Both of them are on nitrogen. You can't get lazy and just say N-dimethyl, because the other methyl could be someplace else. If you say N-N, they're definitely both on the nitrogen, and you have no problem in terms of ambiguity. So, nitriles at the bottom. These are fairly obvious because you have just simply a nitrile name. The end of it is nitrile. It's related to what you start with. In this example, we've got acetic acid with two carbons, so we get acetonitrile. It's a very useful solvent. I think we saw that when we did SN2 chemistry last year. It's a very good polar aprotic. On the right-hand side, we have benzoic acid, and then we have benzonitrile, in which we've now converted this into the C triple bond N type of structure. Nothing too tricky about that. Spend a few minutes on it. Just be comfortable with it. But one of the comments I always get from the biochemists is that students coming out of the sophomore organic class aren't really comfortable with functional groups. Make sure that you understand the names and what they look like, especially when you're going into biochem. Right, what we really want to play with today is this idea of reactivity. We want to talk about what they're used for. And we'll see that there is a sort of a pattern here in which the chlorides and the anhydrides tend to be very reactive with nucleophiles. Esters tend to be less reactive, you can make them react, and amides tend to be the least reactive, and therefore they're the most stable. That's going to be useful because let's say you want to make some clothes or something, you think about polyamides and nylon and stuff like that. You don't want to make clothing out of anhydrides, because as soon as you walk out into the rain, it'll dissolve. It could be embarrassing, all right? So we tend to make things like clothing and bottles and polyester bottles for drinks and stuff like that. We tend to make them out of esters, we tend to make them out of amides because they are stable, and it takes some effort to hydrolyze them. And that can be a good thing or a bad thing. Yes, they're stable, but maybe they're difficult to get rid of. So in terms of recycling these things, can you come up with some systems in which you get the benefit of both? They're stable enough, but they're reactive enough to be able to recycle them and then use the starting materials over again. So there's a fact. A lot of this will be to do with the fact that these materials at the top have very good leaving groups, and down here we have less, the leaving groups aren't as good, but also to do with something about the sort of level of delocalization of the lone pairs. Each of these molecules has that atom attached, and you have at least one lone pair on that atom. And that lone pair can delocalize into the carbonyl. And the argument about how stable these things are would be largely to do with how effective that is. If you have great delocalization, it'll be quite stable. If you have little delocalization, it'll be unstable, and therefore more reactive. On the left, the picture here is trying to discuss the reactivity of these materials versus aldehydes or ketones. And that's a big difference. The aldehyde or ketone did not have a leaving group attached. And this is where you'll get lost if you're not studying enough. We did acetals, we did hydrates, we did imines, we did enamines, all with aldehydes and ketones. We're about to do very similar things with carboxylic acids. And unfortunately, they are so similar, but different enough to cause confusion. So we have this extra atom, and I would argue that each of these atoms, chlorine, oxygen, and nitrogen, are more electronegative than the carbon they're attached to. So they ought to pull electron density away from the carbonyl in terms of the dipole here. So this carbon right there is quite positive. We'll write delta positive there and we'll attack it. But the difference now with the aldehydes and ketones is this group can break off. We didn't have that possibility with aldehydes and ketones. That's the big difference. So we need to worry about why we have different reactivities. If we have different atoms attached, why are they different in terms of their reactivities? And this will be logical. A lot of this will be logical. It turns out we need to think about things like resonance possibilities in these structures. Acid chloride at the top versus the amide at the bottom. We're all comfortable now, I think, with the fact that any carbonyl will be polar. Any carbonyl is polarized because we can take electron density away from carbon and we can draw a resonance structure like this in the middle, in which the carbonyl carbon looks like a carbocation. And we've argued that in recitation quite often about the fact that these species are resonance stabilized cations, if you think of it that way. So now we have to think about, okay, we have a carbocation type structure right there. That needs help. It needs help from electron dense species. So I have next door right here, unlike aldehydes and ketones, I have some element, some atom that can push electrons into that carbocation. Now you're going to get maybe this resonance structure, but go back to the argument about benzene and bromobenzene and chlorobenzene. They were deactivating groups, but they were orthopyrodirectors. And a lot of this was to do with the size of the atom. Chlorine's large compared to carbon. Bromine's large compared to carbon. So the overlap between those atoms, if they are neighbors, isn't great. Okay? There's a mismatch in terms of their size. So the argument here is that this resonance structure isn't that big of a deal for this system, because the chlorine really is quite large and is not very good at overlapping. It does help a little bit, but not as well as some of the other systems that I'll show you now. So because of chlorine being larger, or bromine, we don't do iodides, they're too unstable, but bromides we can do, chlorides we certainly use a lot of. This isn't as stable at the top as the one at the bottom because of the size of the chlorine. So it goes all the way back to the first week or first couple of weeks when we laid out the rules of the subject, and it's similar now. Down at the bottom, we have a system again, if we split this, so we draw a resonance structure at the bottom in which the carbonyl looks like a stabilized carbocation. Next door we have a nitrogen. Now nitrogen is fine at sharing a pair of electrons. In fact, if you think about esters versus amides, which is more basic, N or O? Which is more nucleophilic, N or O? Nitrogen's more nucleophilic, nitrogen's more basic. What was the background to that? It's better at giving electrons away. What was the background between N and O? Electronegativity, right? N is less electronegative, so it's easier to share that lone pair. It always goes back to the very basics. So it turns out this is quite good at donating electron density, and it happens to be very similar in size to the carbon next to it. So you have no problem here in terms of overlap like you do at the top, and you get a very good structure here in which this really does help. It's significant. So the argument now is that the anhydrides and the chlorides, I should stop there. The chlorides are so reactive and less stable because of less electron help from next door, whereas the amides at the bottom and also the esters, you get significant help from next door from the atom here, the N, or in the ester case, the O. So that's the background to it. Now, we need to worry about things like why these things are reactive. We need to worry about what shape they are. We need to worry about what they really look like. Are they really sp2 and sp3 carbons and nitrogens, or are they somewhere in between? So you will find in biochem that this little picture becomes a lot of the material you have to worry about. We have an amide, carbonyl, nitrogen, a couple of R groups, or an H, right? You can have hydrogen bonding all over the place, that's why they're useful, and it's a significantly strong bond. What shape does it look like right there? What's the shape here? What's it trying to show you with that picture? Looks like it's flat, looks like it's planar, and it most likely is. Because if you look at the resonance structures over here, that looks like it's sp2, and in this resonance structure, that looks like it's sp2 as well. So the answer is it's somewhere in between sp2 and sp3. And if you look at a simple system like this, that looks like it's all flat, which suggests that this nitrogen isn't sp3, it's sp2. How does that come? Where does that come from? That picture right there, you see it? It's sp2 in that structure, in that picture. So this is planar. And if it's planar, and you have sort of a possible rotation around here, we might suggest that that rotation is slow. You think about butadiene when we had double bonds next to each other, and we had the S-cis and the S-trans, and we talked about the rotation around that single bond, the S being the sigma bond. And that rotation was slow, but you could go from S-cis to S-trans and backwards. It's very similar here. If I have a setup here where I'm delocalizing from nitrogen and I have a significant amount of double bond character between the C and the N, what does that mean? It means that picture right there, a significant amount of double bond character, then the rotation around that bond ought to be slow. And it is. And there's a significant actual energy to get from one to the other. So I've got a system here where the R groups are pointing in opposite direction. What might you call that? E, yeah? Or S-trans, maybe, if it's a conformation, S-trans. And if we rotate around and the R groups are in the same direction around that single bond, what might we call that? It's not a trick question. S-cis. S-cis, you can use the same language. So the idea here is that there is a significant amount of activation barrier to go from one to the other. Why is that? Because in between the carbonyl and the nitrogen, you have delocalization. You have pi character, like you did with 1,3-butadiene. And that all comes about because of these resonance structures, which are showing delocalization, stabilization, help from the adjacent atom. You wouldn't get that in an aldehyde or a ketone because there's no lone pair there. So keep an eye on that. That will be important. Put an asterisk. That is biochemistry right there. Well, we need a mechanism. We need to worry about how these things react. When we did aldehydes and ketones, they added things. You did not lose the R groups. You did not lose the hydrogen. They simply added things. So that was nucleophilic addition. Now what we're going to do is replace things. Because we have a chloride. Chloride's a great leaving group. Bromine. Bromine's a great leaving group. We can replace these things in substitution reactions. So in this example, whatever Z or Z happens to be, you can replace it. You couldn't do that over here with the aldehydes and ketones. They're all full leaving groups so far. Okay? I'll stop there. I'll leave that until next week. You cannot replace these things just yet. So here's the mechanism, or here's the overall process, I should say. There's an acid chloride, or there's an acid anhydride, or an ester, or an amide. And we bring in a nucleophile, and we're going to boot out whatever Z happens to be, and end up with a substituted product and the leaving group. So you have to go back and worry about what's a good leaving group. What helps stabilize leaving groups? Size. What else? What else stabilizes charge? If you're kicking out something that's negative, what would you like it to do? Share electrons. What's that called? Begins with res. Resonance. Thank you. So if you can delocalize that charge, that would be a good leaving group. So here we go. This slide, but I think it's a way of keeping everything in shape, keeping everything sort of organized. On the left and the right, from chapter 20, we did not kick out any leaving groups because there weren't any leaving groups. We did additions where nucleophiles went in, imagine a grignard going in or a hydride going in, and we simply added and they stuck. And those types of processes were irreversible because the nucleophile that went in was a poor leaving group. On the right-hand side is where we are now and where we need to be for the rest of the term. We do have a potential leaving group, whether it be an ester, an acid chloride, an amide, or whatever. That electronegative element is able to break off at some point. So now we will see that nucleophiles come in and they replace whatever happens to be here. And the mechanisms are different, but they're not that complicated until you start to add them together. Until you start to get nucleophilic acyl substitution followed by nucleophilic addition followed by quenching. And what we'll really do from now on is just put things together. There really aren't that many new mechanisms. It's just adding bits and pieces from old mechanisms to get bigger processes. So keep an eye on that. Aldehydes and ketones, don't be kicking anything out. On the right-hand side, that's the whole point. Nucleophilic addition on the left, nucleophilic acyl substitution on the right. Okay, so that's in section 21.7. If you've got, as you do have access to my slides, go and have a look at that, and that will help, I would imagine. Okay, here we go. We've seen this. We did this a while back when we did things like ester. We talked about replacing some of the material earlier. We are going to start out with a nucleophile. We're going to have either a chloride or an anhydride, whatever attached here, and we're going to replace it with a nucleophile. So mechanistically at the bottom, our nucleophile typically is going to be something negative. It might be under acidic conditions, but the same rules apply. In recitation, we've been trying to say, if you can identify acidic conditions, what charges will your intermediates be? Positive, H+, positive, right? If you can identify basic conditions, what are we going to do there? Everything would be negative. We see both here. Got to keep organized. So in this example, we have some nucleophile which is defined as being negative. Therefore, this is basic. And so we're going to see negative pieces along the reaction profile. And what will happen here is the nucleophile, which is electron-rich, will go after the carbonyl carbon, which is electron-poor. And we will push electron density up onto the O as an electron sink, somewhere to put the electron density. But it turns out these types of things aren't going to be stable most of the time. We're going to come back down and kick out the leaving group, and we end up with a substitution product. Now, what shape is this thing in the middle? Tetrahedral. And it's an intermediate, so let's call it a tetrahedral intermediate. Biochemistry is full of these things. Tetrahedral intermediates are everywhere. So we're going to see now nucleophilic attack, formation of an intermediate species, collapse of the intermediate species, formation of the carbonyl. You're swapping whatever the nucleophile was for whatever the leaving group is, and you have access now to new material. Examples. Here we have a simple acid chloride. React an acid chloride with an alkoxide, like here, methoxide. What else can methoxide behave as? A base. In this system, you don't see any acidic protons, so the nucleophilic substitution seems to be the most sensible thing to do. And we will think about this in terms of the overall process and think about maybe why it's not so reversible. In this example, this is a nucleophile. It goes after the carbonyl. It forms a tetrahedral intermediate. Now, you have a choice here of kicking out either a chloride or kicking out a methoxide. Which do you think is better? Chloride. Chloride is much better at taking a charge than O. So we're going to kick this out in the second step here, loss of the leaving group here to form the carbonyl, chloride breaking off right there. And that gives us a pretty good material. And if you go back to that chart about which was better and more stable, the ester is more stable than the chloride. So the right-hand side is heavily favored. On top of that, okay, can we go backwards? We've been making this decision in recitation. We've been trying to work out how to think about these things logically instead of memorizing everything. This is an okay nucleophile, right? It's a decent nucleophile. It could go back after here, and it could end up back up there. But then, are you likely to kick out methoxide? No, it's very basic, and it's not that stable. You're more likely to kick out chloride and end up back here. So even if it is a little bit reversible, you're going to end up in the same place because that's the best place to be. Keep an eye on that. That's the mechanism for basic type of reactions in which you're talking about some nucleophile which is negative, going after a carbonyl, and then kicking out a leaving group. In this system, we've got to be careful here in terms of organization. This example is hydrolysis. And what the textbook is trying to do at this point is just think about the different conditions that you could experience in this type of system. Very much like we did with the acetals and we did with the imines and enamines. If we have acid, things tend to be protonated, things tend to become positive. If we have base, we tend to get nucleophilic attack and things become negative. So this slide is trying to show the consequences. I'm not going to show you the full mechanism, that comes later, of the reaction between an ester and water in the presence of an acid. And what tends to happen here is that this OR group, O-methyl, O-ethyl, O-propyl, whatever, tends to get broken off and you end up with an OH group. So it's a replacement reaction. But the conditions now are different, and that's what we've been working on in recitation is identifying these conditions. If you have a proton available, guess what you're going to do first? Protonate something. Now, in this case, we have a small amount of acid. We have a catalytic amount of acid. Why do we think that is catalytic? What's the basis for that? Well, it turns out if you don't have the acid, that's a very, very slow process. Adding the acid speeds things up, but you've also got to get the acid back if it's catalytic. And that's why you only need a small amount, because you keep recycling it. First thing you do is protonate. Well, that's that first step here, isn't it? It looks an awful lot like the first step in the ketone reaction to give an acetal. That is the same step. But that's a problem, because all of a sudden, it's like, whoa, acetals, esters, amides, it all starts to look alike, unless you're organized. Why is this more reactive now? What might you draw after this picture to show why this species is more reactive than it was? A resonance structure. You draw a resonance structure possibly where this carbon down here becomes positive. And then you might draw another resonance structure in which this lone pair from the O helps that out. But no doubt, this protonated species is more electrophilic and therefore more reactive than the species above it. You protonated it. Oxygen wants its electrons back, and so where oxygen was electronegative at the top, it's more electronegative now because it's positive, and it's going to take it out on the carbon next door. So that carbon needs some help. So it sees water. Water comes in now. Is water a strong nucleophile or a weak nucleophile? It's weak, but it's strong enough because we enhance the reactivity of the ester component. So we can go after that with a nucleophile, we can add to this, and that is starting to look like something we just drew. What is that? What shape is it? Tetrahedral. So let's call it a tetrahedral intermediate. What do you think happens next? And I'm not going to do the whole mechanism here, that's coming up next week. Just for those who are getting this stuff, what do you think happens next? Proton transfer. To make this a good leaving group, we'll break it off, and we'll end up with a carboxylic acid. If you're at that stage where you see this is fun. And it really is sort of, you get better at this stuff, and you start to understand things so you can use it in a positive sense and a proactive sense. Well, the graph on the right is trying to show the difference in the reactivities between the different species, and we can now see this is higher. This species now is higher in energy, it's less stable, more reactive. And then along the reaction profile, we're picking up this third group right here, and it's trying to show you that this species is unstable. We're not going to see an awful lot of species that have 3 oxygens attached. It's not a good system. So now we have the possibility now of catalysis using acidic conditions analogous to what we did with the acetals and aldehydes and ketones. So what do you do now? What's the other one to try? base. The difference in this is that, we think of acid as being attacked. We think of nucleophiles as doing the attacking. It switches kind of roles. So if you were to dump in some hydroxide into a flask and a beaker, and you put your hand in there, what would happen? It would hurt like hell, right? Because the hydroxide is going after your hand. It's very aggressive. It's either basic or it's nucleophilic, both of which it's very good at. So in this case, I don't need any help. In the previous slide, we had to make this thing more reactive so this thing would be interested. In this reaction, this is interested from the get-go. So we have a nucleophile looking to attack something. Attack, attack, attack. It wants to go after the carbonyl carbon. The carbonyl carbon is the most positive part of that. So let's go after it. What do you think this looks like? Tetrahedral intermediate, it is. Now that thing can collapse, and we'll see that a little bit later when this thing comes back down and this thing breaks off, when we finish those mechanisms off. But they do parallel, I would argue, the acetal and hydrate chemistry. Okay, that's pretty much it in terms of the discussion so far. Acid catalyzed processes involve positive charged things. Base processes involve negatively charged things, and that's consistent all the way through. Well, think about what we've done recently. We used acid chlorides in Friedel-Crafts acylation reactions, so now you can go back and make them. You will find that this 38-step reaction sequence that I'll bring in next week to start thinking about it is all based on the loops and all based on going between the different families. In this example here, we can go back to a carboxylic acid now and make that acid chloride that we used in the Friedel-Crafts reactions. And you can make the carboxylic acid from a primary alcohol. And you can make the primary alcohol from a bromide or something, which you can make from an alkane, which you can get from the ground. So now we can go all the way back to crude oil in terms of doing synthesis. Well, what you get here is a reaction in which carboxylic acid reacts with SOCl2. It gives you an acid chloride, SO2. Anybody know anything about SO2? Its physical properties? It's a gas. It's a gas, so it disappears. Makes it irreversible because it's a gas. It doesn't come back. And so if it's not there as a reagent, you can't go backwards. And you get HCl. And this is a really nice reaction to run. This is a liquid. You just boil the things together and you get the acid chloride. Distill it away and you get the product. So that's how we make them. Mechanistically, yeah, we'll do it. It's on my website, and this is somewhat similar to things you've already seen. Where last semester did you see sulfur doubly bonded to oxygen reacting in some type of chemistry? TSCl, yeah? Tosyl chloride. Tosyl chloride. Go back and look at that mechanism. It's very similar to this. The sulfur in the middle here, you would expect to be quite electrophilic. In other words, it needs some help. It has all these electronegative elements attached, which are pulling electron density away from the sulfur, and so we expect the nucleophile to want to go after the sulfur. And indeed it does. This carboxylic acid, you can see this extra arrow here, that's a little bit of extra help. That makes this thing fairly nucleophilic because I can push electron density in such a way that the carbonyl becomes more nucleophilic. And I'm going to attach the two pieces together at sulfur and end up with this. That is a species which looks like it has four things attached, which doesn't last very long. What would we call it? It's a tetrahedral intermediate. It doesn't look like the one on the previous slide. It doesn't have, there's not any carbon in it. But that's what it is. It's a tetrahedral intermediate. It's using the same principles. So now this collapses, and it collapses because chlorine's a good leaving group. I want to get the charge off the oxygen and attach to the chlorine. That's exactly what happens there, and we end up with this. That looks an awful lot like a tosylate from last year. Very, very similar. Now we need to make HCl. We can simply deprotonate that. You don't really use any solvents here, or any, because it's a liquid itself, SOCl2, you don't need to. Chlorine can come in, you've got HCl right there, and all of a sudden we're now at the stage where we can produce the chloride. So why do you think this is such a good leaving group? What's asking to happen here is that this O breaks off and becomes negative. Why should it be a good leaving group? Resonance stabilized. It is resonance stabilized if it breaks off. So at the bottom, that's what will happen. This is just expanded out. This is this species right here. Chloride comes in. I've still got Cl minus left over. Comes in, attacks the carbonyl, boots that up to there. Give me a discussion of that, or a description of that. What does this remind you of? What does it look like? Tetrahedral intermediate. Again, we have a leaving group attached. This leaving group now happens to be the sulfur, the SO, which then is delocalized, and you can see where the extra chloride comes from, and you get SO2 gas, and you end up with a chloride. You need to know that mechanism because it's very similar to other things we've done. And that's how you make acid chlorides. Very simple reaction to run, and a very high yielding process, and it gives you access now to some very, very useful materials with good leaving groups attached. The problem with acid chlorides when you buy them, if you work in an organic lab, be very careful. They are very reactive with water, simply because water is a nucleophile, chloride's a leaving group, and on the right-hand side of the equation you get a carboxylic acid, which is more stable, and you get HCl. So if you leave a bottle of acid chloride open, and you come back after the weekend, it probably isn't all acid chloride anymore. It got hydrolyzed. So we wrap these things up, we tighten the top when we put it back on, and we put parafilm around and make sure that the thing is watertight, waterproof. Now mechanistically, I don't see any bases necessarily, I don't see any acids, I just see this thing and I see this thing. If you're getting better at this, it should be straightforward in terms of interpreting what might happen here. This is the nucleophile, put the lone pair on there. This is the leaving group, we'll break it off. We're going to attack. There's the first attack. What does that remind you of? What is this? Tetrahedral intermediates. Every time it's nucleophilic acyl substitution, it's a tetrahedral intermediate. And this can break off and go backwards, sure, because water's a decent leaving group, but if we break off the chloride, that's a better leaving group, and that will give us over here this species, which then has to lose a proton, and we're done. We have a carboxylic acid. What is useful is this. Acid chlorides react well with alcohols. Very similar to the way it just happened with the water. The water's useless because you get the carboxylic acid back. But if you want to do this in a synthetic sense, the chloride will break off and the alcohol comes in and you get an ester. It's a very, very useful way of making esters. You start off with alcohol, be it primary or secondary. I'll show you in the bottom, you can control these things. We'll understand what happened down at the bottom. And you use the acid chloride, but in this case you need something called pyridine. What was pyridine used as? It's a base. It's a weak base and also a decent solvent. So this serves two purposes. Now what do you think the base picks up? What is the byproduct that needs to be picked up? HCl, yeah? H from there, Cl from there. So now we've got this argument that the pyridine serves a couple of purposes, and you're able to go from here, attack this thing, pick up the proton with the pyridine, lose the chloride, and you end up with an ester through nucleophilic acyl substitution, through a tetrahedral intermediate. Now, very last comment today, and then we'll come back to it on Monday. Why has this, you probably have to run this at lower temperature, but why has this gone for this O and not the other O? It seems to have selectively gone for this end of the molecule and not that end of the molecule. Any ideas? Crowding. Secondary alcohols are more crowded, therefore less reactive in these conditions. That's a primary alcohol, and so you're getting some selectivity, simply based on the environment.